Imagine standing in a darkened room, holding a flashlight. You flip the switch and instantly, a beam of light cuts through the darkness. What you're witnessing is one of the universe's most fundamental phenomena, yet also one of its most mysterious. Light, this seemingly simple thing that allows you to see the world around you, is actually a complex dance of energy and matter that has puzzled scientists for centuries. Light is not what it appears to be. When you see that beam from your flashlight, you might think of it as a continuous stream, like water flowing from a hose. But zoom in close enough, impossibly close, and you'd discover something extraordinary. Light is made of tiny packets of energy called photons. These photons are like invisible messengers, carrying energy from one place to another at the ultimate speed limit of our universe, 300 million meters per second. Each photon is a quantum of electromagnetic energy, a discrete bundle that cannot be divided further. When your flashlight produces light, it's actually firing trillions upon trillions of these photons in a continuous barrage. They emerge from the bulb, travel through space, bounce off objects, and eventually strike your eyes, where they're converted into the electrical signals your brain interprets as vision. But here's where things get truly strange. These photons behave like particles when we try to detect them individually, yet they also behave like waves when we're not looking. This isn't just a limitation of our instruments or understanding. It's a fundamental property of reality itself. Light exists in a state of duality that defies our everyday experience. Picture throwing a stone into a calm pond. The ripples that spread outward are waves with peaks and troughs that can interfere with each other, creating patterns of reinforcement and cancellation. Light behaves exactly like these water waves in many circumstances. It has a wavelength, the distance between successive peaks, and a frequency, how many peaks pass a given point each second. When two light waves meet, they can add together to create brighter regions or cancel each other out to create darkness. Yet when we build detectors sensitive enough to catch individual photons, light reveals its particle nature. Each photon arrives as a discrete event, like a marble dropping into a bucket. You can count them one by one. A dim light source might emit only a few photons per second, while a bright laser sends out countless billions. This wave-particle duality isn't just an academic curiosity. It's the foundation that makes everything from solar panels to computer chips possible. The photoelectric effect, discovered by Albert Einstein and for which he won the Nobel Prize, depends entirely on light's particle nature. When photons strike certain materials, they can knock electrons loose, creating an electric current. This is how solar panels convert sunlight into electricity. The energy of each photon depends on its wavelength, and this relationship gives rise to the electromagnetic spectrum. The light your eyes can see represents only a tiny sliver of this vast spectrum. What we call visible light spans wavelengths from about 400 nanometers for violet light to 700 nanometers for red light. A nanometer is incredibly small, roughly the width of 3 atoms placed side by side. Beyond red light, we find infrared radiation, the heat you feel from a warm fire, or radiating from your body. Stretch the wavelengths even further, and you encounter microwaves, the same type of electromagnetic radiation that heats your food, and radio waves that carry signals to your phone and radio. In the other direction, beyond violet, lies ultraviolet light, the invisible radiation from the sun that can burn your skin and cause materials to fluoresce with brilliant colors. Push to even shorter wavelengths, and you find X-rays, capable of penetrating flesh but not bone, making them invaluable for medical imaging. At the extreme short wavelength end of the spectrum lie gamma rays, so energetic they can alter the very atoms they strike. All of these forms of electromagnetic radiation are essentially the same phenomenon as visible light. They're all composed of photons, differing only in their energy and wavelength. A radio wave photon carries much less energy than an X-ray photon, but they're fundamentally the same type of particle. When light encounters matter, the interaction depends critically on the energy of the photons and the structure of the material. Low-energy photons, like those from radio waves, tend to pass through most materials with little effect. The walls of your house are essentially transparent to radio waves, which is why you can receive radio signals indoors. Higher energy visible light photons interact more strongly with matter. They can be absorbed, causing electrons in atoms to jump to higher energy levels. This absorption is what gives materials their color. A red apple appears red because it absorbs most wavelengths of visible light, but reflects red wavelengths back to your eyes. Some materials are transparent to visible light, allowing photons to pass through with minimal interaction. In glass, the photons aren't absorbed, but they do slow down slightly as they pass through, bending their path in the process we call refraction. This bending is what makes lenses possible and gives us eyeglasses, telescopes, and microscopes. Other materials are opaque, absorbing most of the light that hits them. The absorbed energy doesn't just disappear, it's converted into heat, causing the material to warm up. This is why standing in bright sunlight makes you feel warm. Your body is absorbing countless photons and converting their energy into thermal motion of your atoms. At the atomic level, these interactions are governed by the electromagnetic force, one of the 4 fundamental forces of nature. When a photon encounters an atom, it can interact with the electrons orbiting the nucleus. The exact nature of this interaction depends on the photon's energy and the atom's electronic structure. In metals, electrons are loosely bound and can move relatively freely. This creates a kind of electron sea that can respond very quickly to electromagnetic fields. When light hits a metal surface, these free electrons oscillate in response to the light's electric field. As they oscillate, they generate their own electromagnetic waves, effectively re-radiating the light back into space. This is the basic mechanism of reflection. The quality and intensity of reflection depend on how well the electrons can respond to the incoming light. Perfect conductors would reflect all electromagnetic radiation perfectly. Real metals fall short of this ideal, absorbing some fraction of the incident light and converting it to heat. But metals aren't the only materials that can reflect light. Many non-metallic surfaces also reflect light, though through different mechanisms. Even transparent materials like glass reflect a portion of incident light at their surfaces. This is why you can see your reflection in a window, even though most of the light passes through. The percentage of light reflected depends on the optical properties of the material and the angle at which light strikes the surface. These properties are described by the material's refractive index, a number that characterizes how light propagates through the material compared to its speed in vacuum. When light travels from one material to another, say from air into glass, some of it reflects at the boundary, while the rest continues into the new material. The proportions depend on the difference in refractive indices and the angle of incidence. At certain angles, called Brewster's angle, the reflected light becomes completely polarized, with its electric field oscillating in a specific direction. Understanding these interactions between light and matter has revolutionized human civilization. It gave us photography, allowing us to capture images by controlling how light exposes photosensitive materials. It led to the development of lasers, devices that produce intense, coherent beams of light with applications ranging from surgery to telecommunications to entertainment. The study of light has also revealed fundamental truths about the universe itself. By analyzing the light from distant stars and galaxies, astronomers have mapped the cosmos and discovered that the universe is expanding. The slight shifts in color of this cosmic light tell us about the motion of celestial objects and the very fabric of space-time. Mirrors occupy a special place in this story of light and matter. They represent the ultimate triumph of reflection, surfaces engineered to send light back along precisely controlled paths. But even the best mirrors we can create fall short of perfection. They absorb some light, convert some energy to heat, and introduce subtle distortions. This imperfection isn't just a technical limitation. It reflects deep truths about the nature of matter and energy. Real materials, no matter how carefully prepared, always have some disorder, some impurities, some quantum mechanical uncertainty that prevents perfect behavior. Yet scientists and engineers continue pushing the boundaries, creating mirrors with reflectivities that exceed 99.9%. These nearly perfect mirrors enable precision experiments that probe the fundamental laws of physics, from detecting gravitational waves to confining light in optical cavities for quantum computing. But what if we could go further? What if we could imagine a truly perfect mirror, one that reflects 100% of incident light with no absorption, no scattering, no loss whatsoever? Such a mirror would represent more than just an engineering achievement. It would be a window into the deepest principles governing light and matter, energy and information in our universe. To understand what happens when light encounters this hypothetical perfect mirror, we must first understand how ordinary mirrors work and why they are not quite perfect. Walk into any bathroom and you'll find one of humanity's most familiar yet remarkable inventions hanging on the wall. The mirror seems so simple, so obvious in its function, that we rarely pause to consider the intricate physics occurring every time we glance at our reflection. Yet this everyday object represents centuries of scientific understanding and technological refinement, a testament to our species' mastery over light itself. The mirror you see each morning is far more complex than it appears. What looks like a single uniform surface is actually a carefully constructed sandwich of materials, each playing a crucial role in capturing and redirecting light. The front surface is glass, typically about 3 to 6 millimeters thick, polished to extraordinary smoothness. Behind this glass lies the true heart of the mirror, a thin, metallic coating that does the actual work of reflection. Most modern mirrors use silver as their reflective coating, though aluminum and other metals are also common. This metallic layer is incredibly thin, often just a few hundred atoms thick, applied through a process called vacuum deposition. In a sealed chamber with all air removed, silver is heated until it vaporizes, then condenses on the glass surface in an atomically thin layer. But even this isn't the complete picture. Behind the silver coating lies yet another layer, typically paint or some other protective backing, designed to prevent the delicate metal film from being damaged by moisture or oxidation. The entire assembly is then sealed at the edges to create a durable product that can withstand years of use. When light from your bathroom fixture strikes this mirror, it first passes through the glass. This might seem trivial, but it's already introducing subtle effects. Glass isn't perfectly transparent. It absorbs a small fraction of light, particularly at certain wavelengths. This is why very thick glass appears slightly greenish. The light is also slowed down as it passes through the glass, traveling at about 2/3 its speed in vacuum. As the light reaches the silver backing, the real magic begins. Silver is an excellent conductor of electricity, which means it contains vast numbers of free electrons that can move easily through the metal's structure. These electrons form what physicists call an electron sea, a dynamic, responsive medium that can react almost instantaneously to electromagnetic fields. When photons strike the silver surface, their oscillating electric fields cause the free electrons to oscillate in response. This creates a kind of electromagnetic dance where the incoming light wave drives electron motion, and the moving electrons generate their own electromagnetic waves. Under ideal conditions, these newly generated waves have exactly the same frequency and wavelength as the original light, but they propagate back toward the glass surface. This process happens incredibly quickly, faster than any mechanical system could respond. The electrons oscillate at the same frequency as the light itself, which for visible light means hundreds of trillions of times per second. The electromagnetic waves they generate interfere constructively with other reflected waves, creating a coherent reflected beam that preserves much of the original light's characteristics. But the word much is crucial here. Real mirrors, even the best ones, never achieve perfect reflection. Some light is inevitably absorbed by the silver coating, converted into heat through interactions with the metal's atomic structure. Some light is scattered in random directions by tiny imperfections in the surface, and some light is actually transmitted through the thin metallic layer, never to return. The percentage of light that gets reflected is called the reflectance, and for a typical household mirror, this number is usually around 85 to 90%. This might sound quite good, but it means that 10 to 15% of the incident light is lost with every reflection. In a brightly lit room, this loss is barely noticeable, but it accumulates quickly if light bounces multiple times. You can observe this yourself with a simple experiment. Hold two mirrors facing each other and look at the infinite series of reflections that appears to stretch into the distance. Notice how each successive image becomes dimmer and dimmer. This isn't just a visual illusion. Each reflection loses some light, and after just a few bounces, the images become noticeably fainter. The glass itself contributes to these losses. When light passes from air into glass, about 4% is reflected at the surface due to the change in refractive index. This reflection occurs both when light enters the glass and when it exits after bouncing off the silver backing. So even before considering the metallic coating, the glass surfaces have already introduced nearly 8% loss. These losses manifest in subtle ways that most people never notice, but that reveal the mirror's imperfect nature. Look carefully at your reflection in a bathroom mirror. Then compare it to what you see in a high-quality mirror in a well-lit store. The difference in brightness and color accuracy can be startling. Cheap mirrors often have a noticeable tint, usually slightly greenish or bluish, due to the optical properties of the glass and variations in the metallic coating. Professional mirrors used in telescopes, laser systems, and precision optics are engineered to much higher standards. They might use specially formulated glass with minimal absorption, metallic coatings optimized for specific wavelengths, and surface polishing accurate to a fraction of a light wavelength. Such mirrors can achieve reflectances of 98 or 99%, but even these represent significant compromises. The fundamental problem is that any real material has atomic structure, and this structure inevitably interacts with light in complex ways. Silver atoms, despite forming an excellent conductor, still absorb some electromagnetic energy. The crystal structure of the metal creates microscopic variations in electron density that scatter light. Thermal motion of atoms introduces random fluctuations that convert coherent light into heat. Temperature affects mirror performance in subtle but measurable ways. As a mirror warms up, the metallic coating expands slightly, changing its optical properties. The increased thermal motion of atoms enhances absorption and scattering. Professional applications sometimes require mirrors to be cooled to very low temperatures to minimize these thermal effects. Even the manufacturing process introduces imperfections that limit performance. The vacuum deposition of silver coating, despite being carefully controlled, results in a film with tiny variations in thickness and density. Dust particles in the deposition chamber can create microscopic shadows or bumps. The glass substrate, no matter how carefully polished, retains surface roughness on atomic scales. These imperfections become more significant as we demand better performance. A mirror that seems perfectly adequate for checking your appearance might be completely unsuitable for a precision laser experiment where every percentage point of reflection matters. The requirements become even more stringent in applications like gravitational wave detection, where mirrors must reflect 99.997% of incident light. Surface contamination represents another ongoing challenge. Even in clean environments, mirrors gradually accumulate dust, oils from fingerprints, and chemical residues from the air. These contaminants create additional absorption and scattering, slowly degrading the mirror's performance over time. Professional mirrors often require regular cleaning with specialized techniques to maintain their specifications. The wavelength of light also affects how well mirrors perform. Silver has excellent reflectance across most of the visible spectrum, but its performance degrades in the ultraviolet range. Aluminum mirrors perform better in the UV, but have slightly lower visible light reflectance. No single metallic coating is optimal across all wavelengths, forcing designers to make compromises based on their specific applications. Some modern mirrors attempt to overcome these limitations through sophisticated designs. Dielectric mirrors use multiple layers of transparent materials, with different refractive indices instead of metallic coatings. By carefully controlling the thickness of each layer, designers can create constructive interference for reflected light, while minimizing absorption losses. Such mirrors can achieve extremely high reflectance, but only over narrow wavelength ranges. Another approach involves combining multiple techniques. Enhanced silver mirrors add dielectric overcoatings to silver films, boosting reflectance while providing protection against tarnishing. These hybrid designs can achieve better performance than either approach alone, but they're more complex and expensive to manufacture. Despite these advances, all real mirrors share a common limitation. They exist in our physical universe, constructed from actual atoms that obey the laws of quantum mechanics and thermodynamics. These laws impose fundamental constraints on what's possible, ensuring that some fraction of incident light will always be lost to absorption, scattering, or transmission. The amount of loss might be small, perhaps just a fraction of a percent for the best mirrors, but it's never zero. This seemingly minor imperfection has profound implications. It means that light energy is continuously converted to heat whenever reflection occurs. It means that information carried by the light is gradually degraded with each bounce. It means that no optical system can achieve perfect efficiency. Yet this imperfection also reveals something beautiful about the physics of light and matter. The interaction between photons and electrons that enables reflection is the same fundamental process that allows atoms to emit and absorb light, enabling chemistry, biology, and ultimately life itself. A perfectly reflective material might be physically impossible, but the imperfect reflection we observe is intimately connected to the richness and complexity of our material world. As you stand before your bathroom mirror each morning, you're witnessing the culmination of centuries of human understanding about light and matter. The silvered glass reflects most of the light striking it, creating a recognizable image of yourself. But hidden in that familiar reflection are tiny imperfections, minute losses that reveal the deep physical principles governing our universe. Now imagine if those imperfections could somehow be eliminated entirely. Picture a mirror with zero absorption, zero scattering, zero loss of any kind. Such a perfect mirror would represent more than just a technological achievement. It would embody a fundamentally different relationship between light and matter, one that challenges our understanding of physical law itself. Picture a mirror unlike any that has ever existed or perhaps ever could exist. This is not the silvered glass hanging in your hallway with its subtle losses and minor imperfections. This is something far more extraordinary, a surface that embodies mathematical perfection translated into physical reality. Every single photon that strikes this hypothetical mirror bounces back with perfect fidelity, carrying exactly the same energy exactly the same polarization, exactly the same information it possessed when it arrived. This perfect mirror would reflect 100% of all incident electromagnetic radiation, from the longest radio waves to the most energetic gamma rays. No absorption would occur at any wavelength. No scattering would send photons careening off in random directions. No transmission would allow light to leak through to the other side. Every photon would return along a precisely calculated path, as if time itself had been reversed for that small packet of electromagnetic energy. Such a device would represent the ultimate triumph of human engineering over the fundamental messiness of matter. Real materials are composed of atoms with their clouds of electrons, their thermal vibrations, their quantum mechanical uncertainties. These microscopic imperfections inevitably lead to some interaction with passing electromagnetic radiation. But our perfect mirror transcends these limitations, somehow maintaining a surface that responds to light with mathematical precision. The closest analogy in existing physics might be the concept of a perfect conductor, a material with exactly zero electrical resistance. In such a material, electric current could flow forever without losing energy to heat. Electrons would move through the conductor as if it were completely empty space, encountering no obstacles whatsoever. While perfect conductors don't exist in reality, superconductors at very low temperatures approach this ideal closely enough to enable remarkable technologies. Our perfect mirror would be the optical equivalent of such a perfect conductor. Just as a perfect conductor would carry electric current without loss, the perfect mirror would redirect electromagnetic waves without any energy dissipation. The electrons in its surface would respond to incoming light fields with perfect efficiency, re-radiating electromagnetic waves that exactly cancel the incident radiation while producing a perfect reflected beam. But unlike superconductors, which lose their special properties when warmed above a critical temperature, our perfect mirror would maintain its flawless performance under all conditions. Temperature fluctuations wouldn't affect its reflectance. Chemical corrosion couldn't degrade its surface. Even the intense electromagnetic fields of high-power lasers wouldn't cause any damage or performance degradation. From a materials science perspective, such perfection seems impossible. Every known material interacts with electromagnetic radiation through mechanisms that inevitably lead to some energy loss. Metals absorb light through electron transitions between energy bands. Dielectrics show absorption at frequencies corresponding to molecular vibrations or electronic transitions. Even the smoothest surfaces have atomic scale roughness that causes scattering. The energy absorbed by real materials doesn't simply disappear. Conservation of energy demands that this electromagnetic energy be converted into other forms, typically heat. When you shine a flashlight on a wall, the wall warms slightly as it absorbs some of the light. This warming represents photon energy being converted into the kinetic energy of vibrating atoms. Our perfect mirror would somehow avoid this conversion entirely. Consider what this means for the second law of thermodynamics, which states that entropy, or disorder, must increase in any closed system. When light is absorbed and converted to heat, the organized electromagnetic energy becomes randomized thermal motion, increasing the system's entropy. But if our perfect mirror never absorbs any light, it would seem to avoid this inevitable increase in disorder. This raises profound questions about whether such a perfect mirror could exist without violating fundamental physical principles. Some physicists argue that perfect reflection might be impossible in principle, not just difficult to achieve technologically. The quantum mechanical nature of matter might inherently prevent the kind of perfect electromagnetic response required for lossless reflection. Yet the concept remains useful as a limiting case, a mathematical idealization that helps us understand the behavior of real mirrors. Just as physicists study ideal gases that perfectly obey simple mathematical relationships, even though real gases show small deviations, we can explore the properties of perfect mirrors to gain insight into optical phenomena. If such a mirror could somehow exist, its properties would be extraordinary. Imagine constructing a box with perfectly reflecting interior surfaces. A pulse of light trapped inside such a box would bounce back and forth forever, never losing energy, never fading away. The light would remain as bright and coherent after 1 million bounces as it was when first introduced. This contrasts sharply with real optical cavities, where light intensity decays exponentially with time, as each reflection removes a small fraction of the energy. Even the best laser resonators, with mirror reflectances exceeding 99.99%, allow trapped light to escape or be absorbed within microseconds. Our perfect mirror cavity would have an infinite storage time for electromagnetic energy. The implications extend beyond simple energy storage. Information encoded in the light's properties would also be preserved indefinitely. Complex patterns of intensity, polarization, and phase could circulate within the perfect mirror cavity without any degradation. Such a system might serve as an ideal optical memory, storing vast amounts of data in the form of trapped light waves. Temperature behavior would be equally remarkable. Since our perfect mirror absorbs no electromagnetic energy, it would never warm up when illuminated. You could focus the concentrated output of powerful lasers onto its surface without causing any temperature rise whatsoever. All of that electromagnetic energy would be redirected away from the mirror with perfect efficiency. This thermal property would make perfect mirrors invaluable for high-power optical applications. Current laser systems are often limited by the heating of mirrors and other optical components. As these components warm up, they expand and change shape, degrading the precision of the optical system. Perfect mirrors would eliminate this fundamental limitation entirely. The reflection process itself would occur through an idealized version of the mechanisms we see in real mirrors. Free electrons in the mirror's surface would respond to the oscillating electric fields of incident light by oscillating themselves. But unlike real electrons, which lose some energy to collisions and other dissipative processes, these hypothetical electrons would respond with perfect efficiency. The electromagnetic waves generated by these oscillating electrons would have exactly the right amplitude and phase to perfectly cancel the incident light within the mirror material, while producing a reflected wave with identical properties. This process would occur instantaneously, or more precisely, at the speed of light, with no delays or distortions introduced by the reflection process. Quantum mechanically, every incident photon would be reflected as an identical photon traveling in the mirror direction. The quantum state of the light would be preserved exactly, including subtle properties like entanglement between different photons. This perfect preservation of quantum information might enable new types of quantum computing and communication systems. The angular behavior of our perfect mirror would also be ideal. Real mirrors show slight variations in reflectance depending on the angle at which light strikes their surface. Light hitting at grazing angles might reflect less efficiently than light at normal incidence. Our perfect mirror would show exactly 100% reflectance at all angles, from normal incidence to the most extreme grazing angles. Polarization would be handled with equal perfection. Real metallic mirrors can slightly modify the polarization state of reflected light, particularly at non-normal angles. Dielectric mirrors might be designed to preserve polarization for one specific angle, but show variations at others. The perfect mirror would preserve all polarization states exactly, regardless of incident angle. Even the most exotic properties of light would be perfectly preserved. Orbital angular momentum, where light beams carry a form of rotational motion, would be reflected without any change. Complex beam shapes, like the donut-shaped modes produced by some lasers, would maintain their precise intensity profiles after reflection. The perfect mirror's electromagnetic response would extend seamlessly across all wavelengths. While real mirrors might perform well in visible light but poorly in the infrared or ultraviolet, our hypothetical surface would show identical perfection from radio waves millions of meters long to gamma rays with wavelengths smaller than atomic nuclei. This broadband perfection would enable applications impossible with current technology. A single perfect mirror could serve simultaneously as a radio reflector, an optical mirror, and an X-ray focusing element. Astronomical telescopes could be designed to observe across the entire electromagnetic spectrum using identical mirror surfaces. But perhaps the most intriguing property of the perfect mirror would be its relationship to the fundamental limits of measurement and observation. In quantum mechanics, the act of measurement inevitably disturbs the system being observed. Photons used to probe quantum systems must interact with those systems, transferring momentum and energy in the process. Our perfect mirror might represent a kind of interaction that preserves quantum states perfectly, allowing observation without disturbance. Light reflected from such a surface would carry complete information about its interaction while leaving the mirror itself completely unchanged. This might enable new forms of quantum measurement that circumvent traditional limitations. Yet even as we explore these remarkable properties, we must confront the question of whether such perfection could actually exist in our physical universe. The laws of thermodynamics, the principles of quantum mechanics, and the fundamental nature of matter itself might conspire to make perfect reflection impossible, no matter how advanced our technology becomes. Current physics suggests several mechanisms that might prevent perfect reflection. Quantum fluctuations in the electromagnetic field itself create a background of virtual photons that could interact with any material surface. The uncertainty principle limits how precisely we can know both the position and momentum of electrons, potentially preventing the perfect response required for lossless reflection. Even if we could somehow create a surface that approached perfect reflection arbitrarily closely, we might find that the final increment toward absolute perfection requires infinite energy or violates some fundamental conservation law. The pursuit of perfection often reveals unexpected physical principles, as scientists have discovered in their attempts to approach absolute zero temperature or achieve perfect vacuum. Yet the value of considering perfect mirrors extends far beyond their practical realizability. These hypothetical objects help us understand the limits of what's possible in optics and electromagnetism. They provide a theoretical benchmark against which real mirrors can be compared and improved. They inspire new approaches to mirror design that push closer to the theoretical limits. In the end, the perfect mirror serves as both goal and guide. It represents the ultimate expression of humanity's desire to control and manipulate light, while simultaneously revealing the deep physical principles that govern electromagnetic phenomena. Whether or not such mirrors could ever exist, the attempt to understand their properties illuminates the hidden rules by which light and matter interact in our universe. Now, having established what a perfect mirror might be and why it captures our imagination, we must delve deeper into the fundamental physics of what happens when light encounters any reflective surface. At the most basic level, this interaction involves individual photons meeting individual electrons, a quantum mechanical dance that determines whether electromagnetic energy is absorbed, transmitted, or sent back along a new path. To truly understand what happens when light meets a perfect mirror, we must journey into the quantum realm, where individual photons encounter individual electrons in a dance governed by the fundamental forces of nature. This is not the familiar world of everyday experience, where objects have definite positions and predictable behaviors. This is the strange quantum domain, where particles exist in superposition states, where measurement changes reality, and where the very act of observation plays a crucial role in determining what actually occurs. picture a single photon approaching the surface of our hypothetical perfect mirror. This photon is not a tiny ball bouncing off a solid wall, despite the mental images such descriptions might evoke. Instead, it's a quantum of electromagnetic energy, a ripple in the electromagnetic field that permeates all space. As it approaches the mirror surface, it carries with it a specific energy determined by its frequency, a definite momentum despite having no mass, and a polarization that describes the orientation of its electric field. The mirror surface itself is not simply a smooth, reflective boundary. At the atomic level, it's a complex landscape of nuclei surrounded by clouds of electrons. In a metallic mirror, these electrons form what physicists call a Fermi sea, a quantum mechanical fluid where electrons occupy energy states up to a specific level called the Fermi energy. These electrons are not sitting still, but are in constant motion, constrained by the Pauli exclusion principle that prevents any two electrons from occupying identical quantum states. When our photon approaches this electron sea, something remarkable begins to happen. The photon's oscillating electric field starts to interact with the electrons near the surface. But this interaction doesn't occur in the classical way we might imagine, with the electric field simply pushing and pulling on the electrons like a magnet moving iron filings. Instead, the interaction is fundamentally quantum mechanical, governed by the rules of quantum electrodynamics, or QED. In the QED description, the interaction between photons and electrons occurs through the exchange of virtual particles. These virtual photons are quantum mechanical entities that mediate the electromagnetic force, carrying momentum and energy between the real photon and the electrons in the mirror. Unlike real photons, virtual photons can have properties that would be impossible for free particles, such as masses or energies that don't satisfy the normal relationship between energy and momentum. As the incident photon approaches the surface, its electromagnetic field begins to polarize the electron distribution in the metal. The electrons respond by creating their own electromagnetic field, which propagates both into the metal and back toward the incident photon. This response happens incredibly quickly, essentially instantaneously, from our macroscopic perspective, but the process involves a complex quantum mechanical calculation that accounts for all possible ways the interaction could occur. The key insight from quantum mechanics is that we must consider all possible interaction pathways simultaneously. The photon might interact with an electron near the surface, transferring all its energy and momentum to create an excited electron state. Alternatively, it might penetrate deeper into the metal before interacting. It might even interact with multiple electrons in a correlated way. Quantum mechanics requires us to add up the probability amplitudes for all these possibilities to determine the final outcome. In a perfect conductor, which our perfect mirror resembles, the electrons can respond to electromagnetic fields without any energy loss. This means that when the incident photon's field polarizes the electron distribution, the electrons can oscillate in perfect synchronization with the field without dissipating energy through collisions or other loss mechanisms. These oscillating electrons become sources of electromagnetic radiation themselves. According to classical electrodynamics, any accelerating charge radiates electromagnetic waves. In our quantum mechanical picture, the oscillating electrons create new photons that carry away the energy and momentum of the original incident photon. But here's where the perfect mirror's perfection becomes crucial. In a real metal, the electrons would interact with phonons, which are quantum mechanical vibrations of the crystal lattice, and with other electrons through various scattering processes. These interactions would cause some of the incident photon's energy to be converted into heat, reducing the efficiency of reflection. Our perfect mirror somehow avoids all these loss mechanisms. The electrons respond to the incident electromagnetic field with perfect coherence, creating reflected electromagnetic waves that exactly cancel the incident field within the metal, while producing a perfectly reflected beam in the external medium. The mathematics describing this process involves solving Maxwell's equations with appropriate boundary conditions at the mirror surface. In the perfect conductor limit, the electric field must vanish inside the conductor, which means that the reflected field must exactly cancel the incident field at the surface. This boundary condition determines both the amplitude and phase of the reflected wave. From a quantum field theory perspective, the reflection process can be viewed as the annihilation of the incident photon, accompanied by the creation of a reflected photon with identical energy but opposite momentum component perpendicular to the surface. The parallel momentum component remains unchanged, which is why the angle of incidence equals the angle of reflection. But the quantum mechanical description reveals subtleties that classical wave theory misses. The incident photon doesn't simply bounce off the surface like a ball bouncing off a wall. Instead, there's a finite probability that the photon penetrates some distance into the conductor before being reflected. This penetration depth is related to the skin depth of electromagnetic waves in conductors. Even in a perfect conductor, electromagnetic fields don't vanish abruptly at the surface, but decay exponentially with a characteristic length scale. For a perfect mirror, this penetration would be infinitesimally small, but the quantum mechanical wave function of the photon would still extend slightly into the material before the reflection process occurs. This penetration has important consequences for understanding the reflection process. The photon spends a finite, though very brief time interacting with the electrons in the mirror surface. During this time, there's a correlation between the photon and electron states that represents a form of quantum entanglement. For a perfect reflection, this entanglement must be perfectly reversed, leaving both the photon and the mirror in states indistinguishable from their initial conditions. The timescale for this interaction is determined by the frequency of the light and the response time of the electrons in the conductor. For visible light, the interaction occurs over timescales of femtoseconds, quadrillionths of a second. During this brief interval, the quantum states of photon and electrons become correlated, then separate again as the reflection process completes. Quantum mechanics also provides insight into why perfect reflection might be fundamentally impossible. The Heisenberg uncertainty principle limits how precisely we can know both the position and momentum of particles. This uncertainty applies to the electrons in the mirror, which means their response to electromagnetic fields cannot be perfectly predictable or controllable. Additionally, quantum field theory predicts that even empty space contains virtual particle pairs that spontaneously appear and disappear on extremely short timescales. These quantum fluctuations of the electromagnetic field itself represent a form of noise that might prevent any real material from achieving perfect reflection, no matter how carefully it's designed. The process of reflection also involves conservation laws that must be satisfied exactly. Energy conservation requires that the reflected photon carry exactly the same energy as the incident photon, assuming no energy is absorbed by the mirror. Momentum conservation is more complex because the mirror itself can absorb momentum, but in our perfect mirror scenario, the momentum transfer occurs without any permanent change to the mirror's state. Angular momentum must also be conserved during reflection. Photons can carry both spin angular momentum, related to their polarization, and orbital angular momentum, related to the spatial distribution of their electromagnetic fields. A perfect mirror would preserve both types of angular momentum exactly, reflecting complex light beams with their full angular momentum content intact. The polarization behavior during reflection reveals another aspect of the photon-mirror interaction. When linearly polarized light hits a metallic surface, the component of the electric field parallel to the surface experiences different boundary conditions than the perpendicular component. This can lead to changes in the polarization state upon reflection, even for perfect conductors. However, our perfect mirror would somehow transcend these classical limitations, preserving polarization states exactly regardless of incident angle or polarization direction. This would require a surface response that perfectly adapts to any incident electromagnetic field configuration. From an information theory perspective, perfect reflection represents a completely reversible interaction between light and matter. All information carried by the incident photon, including subtle quantum mechanical properties like superposition states and entanglement correlations, would be preserved in the reflected beam. This reversibility is related to the time reversal symmetry of the underlying electromagnetic interactions. The quantum mechanical description also explains why the simple picture of photons bouncing like balls, while useful for some purposes, misses important aspects of the reflection process. The interaction between photon and electrons involves the creation and annihilation of particles, the exchange of virtual photons, and the temporary correlation of quantum states across the light-matter boundary. In real materials, additional quantum mechanical effects come into play. Band structure in metals and semiconductors creates specific allowed and forbidden energy levels for electrons. Photons with energies matching electronic transitions can be absorbed and re-emitted through processes that introduce delays and energy shifts. Surface states, where electrons are localized near material boundaries, can create additional interaction mechanisms. Our perfect mirror would somehow avoid all these complications, responding to electromagnetic fields in a way that preserves all photon properties, while introducing no delays, no energy shifts, and no quantum mechanical correlations that persist after the reflection process. Whether such perfect response is possible within the laws of physics remains an open question. The answer may depend on details of quantum gravity and other aspects of fundamental physics that are not yet fully understood. Some theoretical physicists suggest that information cannot be perfectly preserved in any physical process, which would make perfect reflection impossible in principle. Others argue that perfect reflection might be achievable under special conditions, perhaps involving exotic states of matter or carefully engineered quantum systems. What's certain is that understanding the quantum mechanical details of photon-mirror interactions has led to remarkable advances in both fundamental physics and practical technology. Techniques for manipulating individual photons, creating entangled light states, and engineering quantum optical devices all depend on precise understanding of how light interacts with matter at the quantum level. These insights reveal that reflection, even by ordinary mirrors, is far more complex and fascinating than everyday experience suggests. The simple act of seeing your reflection involves countless quantum mechanical interactions, each governed by fundamental laws that determine how information and energy flow between light and matter. And at the heart of these interactions lies the question of whether perfect preservation of electromagnetic energy and information is ultimately possible in our physical universe. As we delve deeper into the consequences of perfect reflection, we must consider not just what happens to the light itself, but how the reflection process affects the mirror. Even if no energy is absorbed, the act of reflection still involves forces and momentum transfer that have profound implications for both the light and the reflecting surface. Hold a feather in a beam of bright sunlight, and you might think you're witnessing something purely gentle and insubstantial. Light seems weightless, ethereal, incapable of exerting any mechanical force on physical objects. Yet this perception masks one of the most profound and counterintuitive truths about electromagnetic radiation. Light carries momentum, and when it interacts with matter, it can push, pull, and accelerate objects with measurable force. This radiation pressure, as physicists call it, becomes dramatically amplified when light encounters our hypothetical perfect mirror. The story begins with one of the most famous equations in physics, Einstein's relationship between energy and momentum for massless particles. Even though photons have no rest mass, they carry momentum proportional to their energy divided by the speed of light. For a single photon, this momentum is incredibly tiny, but light beams contain vast numbers of photons, and their collective momentum can produce significant mechanical effects. Consider a flashlight beam containing 1 trillion photons per second. Each individual photon carries a momentum so small that it defies everyday comprehension, roughly 10 to the minus 27 kilogram meters per second for visible light. But multiply this infinitesimal quantity by 1 trillion, and the total momentum becomes measurable. When this beam strikes a surface, it transfers momentum just as surely as a thrown baseball transfers momentum when it hits a catcher's mitt. The key insight is that momentum transfer depends crucially on what happens to the light after it hits the surface. If the surface absorbs all the incident light, converting photon energy into heat, then each photon transfers its full momentum to the surface. The object experiences a force pushing it in the direction the light was originally traveling. This is the principle behind solar sails, those gossamer spacecraft that use stellar radiation pressure for propulsion through the cosmos. But absorption represents only one possibility. When light reflects from a surface, something far more dramatic occurs. The reflected photons travel back in the opposite direction, carrying momentum equal in magnitude but opposite in direction to the incident photons. This reversal of photon momentum means that the momentum transfer to the reflecting surface is doubled compared to absorption. Think of it like catching a baseball versus bouncing a baseball off a wall. When you catch the ball, you absorb its momentum and experience a force equal to the ball's momentum change. But when a ball bounces elastically off a wall, the wall experiences twice as much momentum transfer because the ball's momentum changes from positive to negative, a total change of twice the original momentum. Our perfect mirror represents the ultimate case of this momentum doubling effect. Since it reflects 100% of incident radiation with no absorption whatsoever, every single photon that strikes the surface bounces back with its momentum completely reversed. The momentum transfer to the mirror is exactly twice what it would be for complete absorption. This doubled momentum transfer makes perfect mirrors extraordinarily efficient at converting light energy into mechanical force. A perfect mirror surface illuminated by bright sunlight would experience radiation pressure twice as strong as a perfectly black surface that absorbs all incident light. For typical sunlight intensity, this pressure amounts to about 10 micronewtons per square meter, twice the 4.6 micronewtons experienced by absorbing surfaces. These numbers might seem laughably small, but they scale directly with light intensity. Focus the sun's rays with a lens or mirror, and the radiation pressure increases proportionally. Use a powerful laser instead of sunlight, and the forces can become substantial. Laboratories routinely use laser beams to trap and manipulate microscopic particles through radiation pressure effects, a technique called optical tweezers. The momentum transfer from our perfect mirror occurs through the same quantum mechanical processes we explored in the previous chapter. As photons interact with electrons in the mirror surface, virtual particle exchanges carry momentum between the electromagnetic field and the material. But unlike energy, which can be absorbed and converted to heat, momentum must be conserved exactly in every interaction. When a photon reflects from the perfect mirror, its momentum changes from plus p to minus p, where p represents the component of momentum perpendicular to the surface. The total momentum change is 2p, and by Newton's third law, the mirror must gain momentum equal and opposite to this change. Over time, as countless photons undergo this reflection process, the accumulated momentum transfer creates a steady force, pushing the mirror away from the light source. This force has profound implications for any practical application of perfect mirrors. Unlike ordinary mirrors, which experience both radiation pressure and heating from absorbed light, perfect mirrors would experience pure radiation pressure, with no thermal effects whatsoever. All the mechanical force would arise from momentum transfer, with no energy deposition to complicate the dynamics. For space applications, this creates fascinating possibilities. A spacecraft equipped with perfect mirror surfaces could achieve remarkable efficiency in solar sailing. Current solar sail designs must balance reflectivity against thermal management, as absorbed sunlight heats the sail material and can cause thermal distortion or damage. Perfect mirrors would eliminate these thermal concerns entirely while maximizing momentum transfer. The momentum transfer also depends on the angle at which light strikes the mirror surface. For normal incidents where light hits perpendicular to the surface, the full photon momentum contributes to the force. But for oblique angles, only the component of photon momentum perpendicular to the surface contributes to the normal force, while the parallel component creates a sideways force that tends to slide along the surface. This angular dependence enables sophisticated control strategies for solar sailing spacecraft. By orienting perfect mirror surfaces at carefully chosen angles relative to incoming sunlight, spacecraft designers could generate forces in any desired direction. The perfect mirror's lack of absorption losses would make such maneuvering extremely efficient, limited only by the availability of solar photons. But radiation pressure effects extend far beyond spacecraft propulsion. In high-power laser systems, radiation pressure can cause significant distortion of optical components. Current laser mirrors must be designed with mechanical supports robust enough to withstand these forces while maintaining precise optical alignment. Perfect mirrors would experience the maximum possible radiation pressure for any given laser intensity. The forces involved scale as the square of the electric field amplitude, which means they increase rapidly with laser power. For research lasers producing megawatts or gigawatts of power, radiation pressure can reach substantial levels. A perfect mirror in such a beam would experience forces capable of deforming or displacing optical components unless the mechanical design accounts for these effects. Quantum mechanically, each momentum transfer event represents a discrete interaction between individual photons and the collective electron system of the mirror. The uncertainty principle ensures that we cannot predict exactly when or where each individual photon will reflect. But the statistical average over many photons produces the steady radiation pressure force predicted by classical electromagnetic theory. Interestingly, the momentum transfer process reveals another way that perfect mirrors might be fundamentally impossible. In quantum field theory, momentum conservation must be satisfied not just on average, but in every individual interaction. For perfect reflection to occur, the momentum transfer to the mirror must exactly equal twice the photon momentum for every single photon, with no statistical variations. Real materials have complex internal structure that can accommodate momentum transfer through various mechanisms, including lattice vibrations, electronic excitations, and thermal motion. These mechanisms provide the flexibility needed to satisfy momentum conservation for each individual interaction while maintaining overall coherent reflection. A perfectly rigid, perfectly ordered surface might lack the internal degrees of freedom necessary for this flexibility. The timescale of momentum transfer also raises intriguing questions. Classical electromagnetic theory suggests that radiation pressure should be instantaneous, arising as soon as light begins to reflect from a surface. But quantum mechanics indicates that the reflection process takes a finite time, during which photon and mirror states become temporarily entangled before separating. During this brief interaction time, momentum is not perfectly defined due to the uncertainty principle. The final momentum transfer emerges only when the reflection process completes and the photon separates from the mirror surface. For our perfect mirror, this process would need to occur with perfect efficiency and perfect timing for every photon, a level of coordination that challenges our understanding of quantum mechanics. Temperature effects add another layer of complexity Real mirrors experience thermal fluctuations that cause random motion of surface atoms. These fluctuations affect both the timing and magnitude of momentum transfer events, introducing noise into the radiation pressure force. Perfect mirrors would somehow need to avoid these thermal effects while still accommodating the discrete nature of individual photon interactions. The radiation pressure from perfect mirrors also has implications for fundamental physics experiments. Many precision measurements depend on isolating optical systems from external mechanical disturbances. But radiation pressure represents an unavoidable coupling between electromagnetic fields and mechanical motion, a coupling that becomes strongest for perfect mirrors. This connection between light and mechanical motion lies at the heart of emerging technologies in quantum optomechanics, where researchers use laser light to control the motion of mechanical oscillators at the quantum level. Perfect mirrors would represent the ultimate optomechanical coupling, where every photon interaction produces maximum momentum transfer with no energy dissipation. Such perfect coupling might enable new forms of quantum measurement and control that are impossible with lossy optical components. The momentum transfer could be used to create quantum entanglement between light and mechanical motion, opening possibilities for hybrid quantum systems that combine photonic and mechanical degrees of freedom. Yet the same perfect coupling that enables these advanced applications might also make perfect mirrors impractical for many conventional uses. The doubled radiation pressure compared to absorbing surfaces means that perfect mirrors require more robust mechanical support. The complete absence of energy absorption means that all incident electromagnetic energy must be redirected, potentially creating challenging engineering requirements for high-power applications. As we consider these mechanical effects of perfect reflection, we begin to see how the seemingly simple concept of a perfect mirror creates cascading implications throughout physics and engineering. The momentum transfer that occurs with every reflected photon connects electromagnetic radiation to mechanical motion in the most direct possible way, revealing deep relationships between light, matter, and force. But momentum is just one conserved quantity that must be accounted for in perfect reflection. Energy conservation presents equally profound challenges and opportunities. While momentum transfer can occur without energy loss, the energy budget of perfect reflection raises fundamental questions about thermodynamics, entropy, and the ultimate limits of physical processes in our universe. In the grand theatre of physics, energy plays the role of the ultimate accountant, meticulously tracking every transaction between matter and radiation. No energy can be created or destroyed, only transformed from one form to another, according to the first law of thermodynamics. This fundamental principle governs every interaction in our universe, from the nuclear fusion powering distant stars to the gentle warming of your hands by a campfire. But our hypothetical perfect mirror presents a fascinating challenge to this universal bookkeeping, creating a scenario where energy seems to flow without leaving any trace of its passage. When light strikes any ordinary surface, the energy accounting is straightforward, if not always simple. Some fraction of the incident electromagnetic energy reflects back into space, carrying the same energy it possessed when it arrived. Another fraction transmits through the material, emerging on the other side with possibly altered characteristics, but conserved total energy. The remainder absorbs into the material, where it converts into other forms of energy, primarily heat. This absorbed energy doesn't simply vanish. It becomes kinetic energy of vibrating atoms, increasing the material's temperature. The faster these atoms vibrate, the hotter the material becomes. In extreme cases, absorbed light energy can break chemical bonds, drive photochemical reactions, or even ionize atoms by stripping away their electrons. But in all cases, the energy goes somewhere, transformed, but never destroyed. Our perfect mirror disrupts this familiar pattern by reflecting 100% of incident energy while absorbing absolutely nothing. Every joule of electromagnetic energy that arrives at the surface departs again as reflected radiation. From an energy conservation standpoint, this seems perfectly reasonable. The total energy of the universe remains constant, with electromagnetic energy simply changing direction without changing magnitude. But this apparent simplicity masks profound implications for the second law of thermodynamics, which governs the flow of energy and the increase of entropy in physical systems. The second law states that in any closed system, entropy must either remain constant or increase over time. It can never decrease. This law explains why heat flows from hot objects to cold ones, why perfume spreads throughout a room, and why scrambled eggs never spontaneously unscramble themselves. Entropy, in its most fundamental sense, measures the number of microscopic arrangements that correspond to a given macroscopic state. A highly ordered system, where particles are arranged in specific patterns, has low entropy. A disordered system, where particles are randomly distributed, has high entropy. The second law ensures that isolated systems evolve toward maximum entropy, toward maximum disorder. When ordinary materials absorb light and convert it to heat, they're increasing the entropy of the universe. The organized electromagnetic energy of light, with its coherent electric and magnetic fields, becomes the random kinetic energy of vibrating atoms. This transformation represents a fundamental increase in disorder, as organized energy becomes disorganized thermal motion. Perfect reflection appears to sidestep this entropy increase entirely. The reflected light retains all its original organization, its coherent electromagnetic fields unchanged by the interaction. No energy converts to heat, so no increase in thermal entropy occurs. The mirror itself undergoes no permanent change, returning to exactly its original state after each reflection event. This raises a tantalizing question. Could perfect mirrors violate the second law of thermodynamics? Could they provide a mechanism for maintaining perfect order in electromagnetic fields indefinitely, creating islands of decreased entropy in an otherwise increasingly disordered universe? The answer depends on subtle details of the reflection process and the broader context in which the mirror operates. While the mirror itself might not increase entropy during reflection, we must consider the complete system, including the source of the light and the ultimate destination of the reflected energy. Consider a simple thought experiment. Imagine trapping light inside a box with perfectly reflecting walls. A pulse of laser light, initially containing highly organized electromagnetic energy, bounces back and forth between the mirrors indefinitely. In this scenario, the electromagnetic energy maintains its organization forever, never degrading into heat or other disordered forms. Such a system would seem to violate our everyday experience of entropy increase. In the real world, trapped light decays rapidly as mirrors absorb small fractions of energy with each reflection. The organized electromagnetic energy converts to random thermal motion of atoms in the mirror materials. But our perfect mirror box would preserve electromagnetic organization indefinitely. However, this apparent violation dissolves when we examine the system more carefully. The light trapped in our perfect mirror box remains isolated from the rest of the universe. It carries no information about external conditions and cannot influence anything outside the box. From a thermodynamic perspective, this isolated electromagnetic energy contributes nothing to the entropy of the accessible universe. More significantly, creating such a trapped light system would require external work to establish the initial conditions. Someone must inject the organized light pulse into the box and ensure the mirrors are perfectly aligned and perfectly reflective. This preparation process inevitably increases entropy in the external environment by more than the entropy decrease represented by the trapped organized light. The fundamental insight is that perfect mirrors don't create order from disorder. They can only preserve existing order, and only under very specific conditions. Any practical application of perfect mirrors must account for the entropy cost of creating and maintaining the perfect reflective properties. Real materials become mirrors through manufacturing processes that consume energy and increase entropy. Purifying metals, depositing thin films, and polishing surfaces all require work that increases the disorder of the surrounding environment. A perfect mirror would presumably require even more sophisticated preparation, with correspondingly greater entropy cost. Temperature effects provide another perspective on the energy implications of perfect reflection. When ordinary mirrors absorb light, they warm up, increasing their thermal energy and entropy. This warming can change the mirror's optical properties, potentially degrading its performance over time. Thermal expansion can distort mirror shapes, while temperature-induced stress can cause cracking or other mechanical failures. Perfect mirrors would remain at constant temperature, regardless of incident light intensity. All electromagnetic energy reflects away, leaving no energy to heat the mirror material. This thermal stability could be enormously advantageous for high-power applications, eliminating thermal distortion and enabling more precise optical systems. But this thermal isolation also creates puzzles for statistical mechanics, the microscopic theory that explains how thermal properties emerge from atomic motion. In normal materials, absorbed electromagnetic energy increases the average kinetic energy of atoms, which we perceive as increased temperature. The random thermal motion of atoms represents a reservoir of entropy that can accommodate small amounts of absorbed energy without violating thermodynamic principles. A perfectly reflecting surface would need to remain in perfect thermal equilibrium with its surroundings while simultaneously avoiding any energy exchange with incident electromagnetic radiation. The atoms in the mirror surface would need to maintain their thermal motion at exactly the ambient temperature, neither gaining nor losing energy, despite intense electromagnetic fields driving surface electrons at enormous frequencies. This requirement creates subtle contradictions with our understanding of thermal equilibrium. Normally, objects in thermal equilibrium exchange energy constantly with their surroundings through radiation, conduction, and other mechanisms. The balance between energy absorbed and energy emitted determines the equilibrium temperature. Perfect mirrors would somehow need to maintain this thermal balance while reflecting all electromagnetic radiation perfectly. Quantum mechanics adds additional complexity to the energy accounting. In the quantum description, perfect reflection requires precise interference between incident and reflected electromagnetic waves. This interference must occur not just on average, but for every individual photon interaction. Any deviation from perfect interference would allow some energy absorption, heating the mirror and violating the perfection requirement. The quantum vacuum itself presents challenges for perfect energy conservation. According to quantum field theory, even empty space contains fluctuating electromagnetic fields that appear and disappear on extremely short timescales. These vacuum fluctuations carry energy and can interact with material surfaces through mechanisms like the Casimir effect. Perfect mirrors would need to interact with these vacuum fluctuations in precisely the right way to maintain perfect reflection, while respecting quantum mechanical principles. This might require the mirror surface to have properties that compensate for vacuum effects, potentially including negative energy densities or other exotic characteristics that challenge our understanding of matter. The relationship between perfect reflection and information theory provides yet another perspective on energy conservation. Information itself has thermodynamic properties, with the erasure of information necessarily increasing entropy according to Landauer's principle. Perfect mirrors preserve all information contained in reflected light, including complex patterns of amplitude, phase, and polarization. This perfect information preservation might seem to violate Landauer's principle, which suggests that information processing must increase entropy. However, perfect reflection doesn't process information in the thermodynamic sense. It simply redirects information without reading, copying, or erasing it. The mirror acts as a passive information conduit rather than an active information processor. Nevertheless, maintaining perfect information preservation might require active error correction mechanisms to compensate for quantum fluctuations and other sources of information degradation. Such mechanisms would consume energy and increase entropy, potentially offsetting the apparent entropy decrease from perfect reflection. The practical implications of perfect energy conservation in mirrors extend far beyond academic physics. Current laser systems are limited by thermal effects in optical components. Perfect mirrors would eliminate these thermal limitations entirely, enabling much higher power laser systems with unprecedented precision and stability. Solar energy applications could also benefit dramatically. Perfect mirror solar concentrators would reflect sunlight with no energy loss, achieving theoretical maximum efficiency for focusing solar radiation. Combined with the doubled radiation pressure effects we discussed earlier, perfect mirrors could revolutionize both solar thermal power generation and solar sailing spacecraft propulsion. But these applications would need to account for the fundamental thermodynamic costs of creating and maintaining perfect reflective properties. The energy and entropy required to manufacture perfect mirrors might exceed the benefits gained from their perfect performance, especially if the perfection degrades over time due to contamination, mechanical stress, or quantum mechanical effects. The ultimate question is whether the laws of physics permit perfect energy conservation in reflection processes. Current understanding suggests several mechanisms that might prevent perfect reflection, including quantum vacuum effects, thermal fluctuations, and fundamental limits on material properties. These mechanisms ensure that some fraction of incident energy always converts to heat, maintaining the universal increase in entropy required by the second law of thermodynamics. Yet the pursuit of ever better mirrors continues to push the boundaries of what's possible. Each improvement in mirror technology brings us closer to the theoretical limits while revealing new physics and enabling new applications. Whether or not perfect mirrors can exist, the attempt to understand their energy implications illuminates fundamental principles governing energy, entropy, and information in our universe. As we explore these thermodynamic puzzles, we begin to see that perfect mirrors represent more than just optical devices. They embody questions about the ultimate limits of physical law, the relationship between energy and information, and the possibility of creating perfect order in an inherently disordered universe. These questions lead us to consider not just whether perfect mirrors could exist, but what their existence would mean for our understanding of reality itself. In laboratories around the world, scientists are pushing the boundaries of what's possible in optical reflection, creating mirrors that approach the theoretical perfection we've been exploring. These aren't the simple silvered glass mirrors hanging in your home, but sophisticated devices engineered at the atomic level, using principles that would have seemed like magic just decades ago. Through clever manipulation of materials, structures, and quantum mechanical effects, researchers have achieved reflectivities exceeding 99.999%, tantalizingly close to the perfect reflection that remains just beyond reach. The journey toward perfect mirrors has led scientists deep into the realm of metamaterials, artificially engineered substances with optical properties that don't exist in nature. Unlike conventional materials, where optical properties are determined by the atoms and molecules present, metamaterials derive their behavior from carefully designed microscopic structures that are smaller than the wavelength of light itself. Picture a material composed of tiny metallic antennas, each one precisely shaped and positioned to interact with electromagnetic waves in specific ways. When light encounters this forest of nanoscale structures, it doesn't simply reflect or absorb according to the bulk properties of the metal. Instead, each antenna resonates with the electromagnetic field, creating collective responses that can be engineered to produce almost any desired optical behavior. Some metamaterials can bend light in directions that seem to violate common sense, creating negative refractive indices that make objects appear to be in impossible locations. Others can cloak objects by guiding light around them as if they weren't there at all. For our purposes, the most intriguing metamaterials are those designed to achieve near-perfect reflection across broad wavelength ranges. The key insight behind metamaterial mirrors is that reflection doesn't require metal surfaces in the traditional sense. Instead, it requires structures that can efficiently convert incident electromagnetic waves into outgoing waves with the appropriate amplitude and phase relationships. This conversion can be accomplished through resonant structures that store electromagnetic energy briefly before re-radiating it in precisely controlled directions. Metamaterial designers have created surfaces covered with split-ring resonators, tiny C-shaped metallic structures that act like miniature LC circuits, storing energy in both electric and magnetic fields. By adjusting the size, shape, and spacing of these resonators, engineers can tune the surface to reflect specific wavelengths with extremely high efficiency while maintaining precise control over the phase of reflected light. But metamaterials represent just one approach to achieving near-perfect reflection. Another promising direction involves photonic crystals, materials with periodic variations in refractive index that create photonic band gaps, wavelength ranges where light cannot propagate through the material. When light encounters such a band gap, it has no choice but to reflect, potentially achieving very high reflectivity. Photonic crystals occur naturally in some biological systems. The brilliant iridescent colors of butterfly wings, peacock feathers, and certain beetle shells arise from microscopic photonic crystal structures that reflect specific wavelengths while allowing others to pass through. By mimicking and improving upon these natural designs, scientists have created artificial photonic crystals with precisely controlled optical properties. One particularly elegant approach involves creating one-dimensional photonic crystals through alternating layers of materials with different refractive indices. These structures, known as Bragg mirrors or distributed Bragg reflectors, can achieve extraordinarily high reflectivity by using destructive interference to eliminate transmitted light while enhancing reflection. The physics underlying Bragg mirrors reveals beautiful connections between quantum mechanics and classical wave optics. Each interface between materials with different refractive indices partially reflects incident light. In a conventional mirror, these partial reflections from different depths would interfere randomly, reducing overall efficiency. But in a Bragg mirror, the layer thicknesses are precisely tuned so that all partial reflections interfere constructively. The result is a mirror that can achieve reflectivities approaching 100%, but only over a limited wavelength range determined by the layer thickness and refractive index contrast. By stacking hundreds of alternating layers, each just a fraction of a wavelength thick, engineers can create mirrors with reflectivities exceeding 99.9% for specific colors of light. Advanced Bragg mirrors used in laser systems often incorporate dozens or even hundreds of layers, with each layer thickness controlled to nanometer precision. The manufacturing process requires extraordinary attention to detail, as errors in layer thickness or composition can dramatically degrade performance. Despite these challenges, commercial Bragg mirrors routinely achieve reflectivities that surpass the best metallic mirrors by significant margins. But even these sophisticated structures fall short of true perfection. The materials used to construct photonic crystals inevitably absorb some light, particularly at the wavelengths where they're designed to provide maximum reflection. The interfaces between layers introduce scattering losses due to surface roughness and compositional variations. And the finite number of layers means that some light always manages to penetrate through the structure. The quest for perfect reflection has also led researchers to explore exotic quantum mechanical effects that don't occur in conventional materials. One particularly intriguing possibility involves the use of quantum dots, tiny semiconductor particles that confine electrons in all three spatial dimensions. These artificial atoms can be engineered to have precisely controlled energy levels, enabling custom-designed interactions with light. Arrays of quantum dots could potentially create mirror surfaces with optical properties that adapt dynamically to incident light. By using external electric or magnetic fields to tune the quantum dot energy levels, such mirrors could maintain perfect reflection across varying wavelengths or incident angles. The quantum nature of the dots might also enable perfect preservation of quantum mechanical properties like entanglement and superposition. Another exotic approach involves exploiting the Casimir effect, a quantum mechanical phenomenon arising from fluctuations in the electromagnetic vacuum. Between closely spaced conducting surfaces, these vacuum fluctuations create measurable forces that can be attractive or repulsive depending on the geometry and materials involved. Carefully designed Casimir systems might enable perfect reflection through mechanisms that don't exist in classical physics. The connection between perfect reflection and superconductivity has also attracted significant research attention. Superconductors, materials that conduct electricity with zero resistance when cooled below a critical temperature, also exhibit perfect diamagnetism, completely expelling magnetic fields from their interior. This Meissner effect makes superconductors perfect reflectors for low-frequency electromagnetic radiation. But superconducting mirrors face fundamental limitations at high frequencies. As the frequency of electromagnetic radiation increases toward visible light, even superconductors begin to show losses due to the finite energy gap that creates the superconducting state. Above a characteristic frequency related to this energy gap, superconductors behave more like normal metals, with significant absorption and heating. Recent discoveries in condensed matter physics have revealed new phases of matter that might enable perfect reflection through entirely different mechanisms. Topological insulators, materials that are insulators in their bulk, but conduct electricity on their surfaces, exhibit unusual electromagnetic properties that could potentially be exploited for optical applications. The surface states of topological insulators are protected by fundamental symmetries, making them remarkably robust against disorder and impurities that would normally degrade optical performance. This robustness might enable mirror surfaces that maintain perfect reflection even in the presence of contamination or mechanical damage that would destroy conventional mirrors. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, represents another frontier in exotic optical materials. Despite being only one atom thick, graphene interacts strongly with light across a broad wavelength range. Its unique electronic properties, including massless charge carriers and linear energy-momentum relationships, create optical behaviors that don't occur in conventional materials. Researchers have demonstrated that carefully structured graphene surfaces can achieve very high reflectivity while maintaining the mechanical flexibility and chemical stability that make graphene attractive for many applications. Theoretical studies suggest that perfect graphene structures might approach perfect reflection under specific conditions, though practical limitations related to fabrication and environmental stability remain significant challenges. The role of quantum vacuum fluctuations in limiting perfect reflection has become an active area of research as mirror technology approaches theoretical limits. Even in perfect vacuum, electromagnetic fields fluctuate randomly due to quantum mechanical uncertainty principles. These fluctuations interact with material surfaces through virtual photon exchanges, potentially introducing fundamental limits on achievable reflectivity. Some theoretical work suggests that perfect reflection might require materials with negative energy densities or other exotic properties that violate known energy conditions. Such materials might exist only in extreme environments like the vicinity of black holes or in the early universe, making terrestrial perfect mirrors impossible even in principle. However, other researchers argue that clever engineering of quantum vacuum interactions might actually enhance reflection beyond what's possible with classical materials. By structuring surfaces to modify the local density of electromagnetic vacuum states, it might be possible to suppress the vacuum fluctuations that limit conventional mirrors. Cavity quantum electrodynamics, the study of atoms and photons confined in small volumes, has revealed new mechanisms for controlling light-matter interactions that could potentially enable perfect reflection. When atoms are placed inside optical cavities with dimensions comparable to the wavelength of light, their interaction with electromagnetic fields becomes dramatically enhanced. In such systems, single atoms can influence the reflection and transmission properties of the entire cavity, enabling all optical switching and other nonlinear effects with individual photons. Perfect mirror cavities might enable even more exotic phenomena, such as the storage of individual photons for arbitrarily long times, or the creation of perfectly entangled photon states through interaction with trapped atoms. The practical challenges of creating near-perfect mirrors have driven innovations across multiple fields of science and engineering. Precision manufacturing techniques capable of controlling material properties at the atomic level have enabled mirror fabrication that would have been inconceivable just decades ago. Advanced characterization methods can measure reflectivity with unprecedented accuracy, revealing subtle loss mechanisms that limit performance. Computer modeling using quantum mechanical calculations helps designers understand how atomic scale features influence optical properties, guiding the development of new materials and structures. Machine learning algorithms are beginning to automate the design process, searching vast parameter spaces to identify configurations that maximize reflectivity while satisfying practical constraints. Despite these advances, the gap between the best achievable mirrors and true perfection remains finite and might represent fundamental physical limits rather than merely technological challenges. Each incremental improvement in reflectivity becomes progressively more difficult and expensive, suggesting that perfect reflection might remain forever just beyond reach. Yet the pursuit continues to drive scientific progress and technological innovation. The technologies developed in the quest for perfect mirrors find applications far beyond optics, contributing to advances in materials science, quantum electronics, and precision manufacturing. Whether or not perfect mirrors ultimately prove possible, the journey toward them continues to expand our understanding of light, matter, and the fundamental laws that govern their interaction. As we explore these cutting-edge approaches to nearly perfect reflection, we begin to see how the boundary between science and science fiction continues to shift. Technologies that once seemed impossible are becoming reality, while new theoretical limits emerge to challenge our imagination. The quest for perfect mirrors takes us to the very edge of what's possible in our universe, where the laws of physics themselves become the ultimate constraint on technological achievement. But our exploration of perfect mirrors need not remain confined to earthbound laboratories. The cosmos itself provides a vast theater where electromagnetic radiation encounters matter under conditions impossible to reproduce on Earth. From the event horizons of black holes to the vast expanses between galaxies, space offers natural laboratories for studying reflection and absorption under the most extreme conditions imaginable. Beyond the confines of our terrestrial laboratories, the universe itself provides a magnificent stage for exploring the physics of reflection on scales that dwarf human imagination. Here, in the vast cosmic arena, electromagnetic radiation encounters matter under conditions of temperature, pressure, and gravitational field strength that push the laws of physics to their absolute limits. From the surfaces of neutron stars, where matter exists in states impossible on Earth, to the event horizons of black holes, where space-time itself curves beyond recognition, the cosmos offers natural laboratories for understanding what happens when light meets the most extreme forms of matter. Consider first the ordinary stars that fill our night sky with their gentle twinkle. Each star is essentially a giant ball of plasma, matter so hot that electrons have been stripped from atomic nuclei, creating a sea of charged particles that interact intensely with electromagnetic radiation. The surface of our own sun reaches temperatures of nearly 6,000 degrees Celsius, hot enough to vaporize any known solid material instantly. At these temperatures, matter exists in a state called a plasma, where free electrons and atomic nuclei move independently through space. This plasma behaves very differently from the solid metals we use to make mirrors on Earth. The free electrons in stellar plasma can respond to electromagnetic fields, much like the electrons in metallic mirrors, but the extreme temperature means these electrons are moving at tremendous speeds in random directions. When light generated in the stellar core attempts to escape through this plasma atmosphere, it undergoes countless interactions with free electrons through a process called Thomson's scattering. Each interaction slightly changes the photon's direction and can alter its energy through the Doppler effect. The result is a complex dance where photons gradually work their way from the stellar interior to the surface, a journey that can take thousands of years despite traveling at the speed of light. Remarkably, some of this scattered light does escape to space, carrying with it information about the physical conditions deep within the star. But much of the electromagnetic radiation remains trapped, bouncing between electrons in an intricate process that bears similarities to reflection in a mirror, though far more complex and chaotic than the orderly reflection we've been discussing. Now imagine a star so massive that its gravitational field becomes overwhelming. When such a star exhausts its nuclear fuel, gravity crushes the stellar material to densities that exceed anything possible in terrestrial laboratories. The electrons and protons are forced together so violently that they merge to form neutrons, creating a neutron star with matter density exceeding that of atomic nuclei. The surface of a neutron star represents matter in its most extreme form, compressed to densities of 10 to the 15th kilograms per cubic meter. At these densities, a teaspoon of neutron star material would weigh as much as Mount Everest. The gravitational field at the surface is so intense that light itself is significantly redshifted as it climbs out of the gravitational well. These conditions create electromagnetic properties unlike anything we encounter in normal matter. The immense magnetic fields surrounding neutron stars, often trillions of times stronger than Earth's magnetic field, can affect the polarization and propagation of electromagnetic waves in dramatic ways. Some theoretical models suggest that neutron star surfaces might exhibit nearly perfect reflection for certain types of electromagnetic radiation, creating natural mirrors of extraordinary efficiency. But neutron stars pale in comparison to the most extreme objects in our universe, black holes, where gravity becomes so strong that not even light can escape. The boundary around a black hole, called the event horizon, represents the ultimate anti-mirror. Any electromagnetic radiation that crosses this boundary is doomed to fall toward the central singularity, never to return to the external universe. Yet even black holes exhibit fascinating optical properties. Just outside the event horizon, in a region called the ergosphere, space-time itself is dragged around by the black hole's rotation. Light in this region can gain energy from the black hole's rotation through a process called the Penrose mechanism, effectively extracting rotational energy from the black hole itself. The contrast between black holes and our hypothetical perfect mirrors could not be more stark. While perfect mirrors reflect all incident electromagnetic radiation, Black holes absorb everything that crosses their event horizons. In a sense, black holes represent perfect absorbers, the complete opposite of perfect reflectors. Yet, both objects share the property of interacting with electromagnetic radiation in ways that seem to defy ordinary experience. The study of black hole physics has revealed deep connections between gravity, thermodynamics, and information theory that might shed light on the fundamental limits of reflection processes. Black holes appear to have temperatures and entropies, despite being classical objects in Einstein's theory of general relativity. The information paradox, which asks what happens to information that falls into a black hole, raises questions about whether information can ever be perfectly preserved in any physical process. These cosmic perspectives suggest that perfect reflection might be fundamentally impossible for reasons that go beyond the materials science limitations we've discussed. If information cannot be perfectly preserved even in the extreme conditions near black holes, then the perfect information preservation required for perfect reflection might violate fundamental principles that govern our universe. Moving beyond individual cosmic objects, let's consider the possibility of artificial structures on cosmic scales. The concept of a Dyson sphere, first proposed by physicist Freeman Dyson, envisions a massive structure built around a star to capture all of its energy output. While Dyson originally imagined this as a swarm of energy-collecting satellites, we might consider what would happen if such a structure were made from perfect mirrors. A perfect mirror. Dyson's sphere would create a closed system where electromagnetic radiation could circulate indefinitely without loss. Light from the central star would reflect from the inner surface of the sphere, bounce back and forth countless times, and gradually fill the interior with intense electromagnetic radiation. The energy density within such a structure could grow without limit, constrained only by the energy output of the central star. But this scenario reveals fundamental problems with perfect reflection on cosmic scales. As electromagnetic energy accumulates within the perfect mirror sphere, the radiation pressure we discussed earlier would create enormous forces tending to push the structure apart. The sphere would need to be held together by materials with tensile strengths far exceeding anything known to physics. Moreover, the intense electromagnetic fields within the sphere would eventually become so strong that they would affect the curvature of space-time itself, according to Einstein's general relativity. Electromagnetic stress energy curves space-time just as mass does, and sufficiently intense fields could create gravitational effects that would destabilize the entire structure. These considerations suggest that perfect mirrors might be limited not just by materials, science, or quantum mechanics, but by general relativity itself. The very perfection that makes such mirrors theoretically attractive could lead to their own destruction through gravitational effects or radiation pressure forces. The cosmic microwave background radiation provides another perspective on perfect reflection in the universe. This ancient light, released when the universe first became transparent about 380,000 years after the Big Bang, fills all of space with electromagnetic radiation at a temperature of about 2.7 degrees above absolute zero. If perfect mirrors existed in the early universe, they would have trapped some of this primordial radiation, creating pockets of space with different electromagnetic properties than the smooth cosmic microwave background we observe. The absence of such features in our observations might provide indirect evidence that perfect reflection has never occurred on cosmic scales, either because perfect mirrors are impossible, or because they would be unstable over cosmic time periods. Interstellar and intergalactic space, despite appearing empty, actually contains vast quantities of matter in the form of gas and dust. This material, though extremely dilute by terrestrial standards, can interact with electromagnetic radiation over the enormous distances between stars and galaxies. Dust grains in space both absorb and scatter light, creating complex optical effects that astronomers must account for when studying distant objects. Some of these dust grains have highly reflective surfaces due to their composition and the extreme conditions of space. Ice-covered grains, metallic particles formed in stellar atmospheres, and complex organic molecules can all exhibit strong reflection at specific wavelengths. While none approach perfect reflection, they demonstrate that nature has created reflective surfaces under conditions very different from those on Earth. The possibility of naturally occurring perfect or near perfect reflectors in space has implications for the search for extraterrestrial intelligence. An advanced civilization might use perfect mirrors to create optical signatures that could be detected across interstellar distances. Perfectly reflected laser beams or structured light patterns could serve as beacons announcing the presence of intelligence to other civilizations. Conversely, such a civilization might use perfect mirrors to hide from detection, reflecting electromagnetic radiation in ways that make their star system appear natural to distant observers. The perfect preservation of information in perfect reflection might enable communication systems with capabilities far beyond anything possible with current technology. The extreme environments of space also provide natural laboratories for testing the limits of reflection under conditions impossible to reproduce on Earth. The vacuum of space eliminates atmospheric effects that can limit mirror performance. The absence of gravitational tidal forces in free-falling reference frames might allow more precise control of mirror surfaces than is possible in terrestrial laboratories. Space-based telescopes already exploit some of these advantages, using mirrors that achieve higher performance than their ground-based counterparts. Future space telescopes might push even closer to perfect reflection, enabling observations of cosmic phenomena that remain hidden to current instruments. The James Webb Space Telescope, with its precisely controlled mirrors operating at temperatures below 50 degrees above absolute zero, represents humanity's current pinnacle of space-based optical engineering. Its mirrors achieve reflectivities approaching theoretical limits for their materials and wavelength ranges, demonstrating what's possible when terrestrial manufacturing precision meets the ideal conditions of space. But even these remarkable instruments fall short of perfect reflection, limited by fundamental properties of materials and manufacturing tolerances. The quest for perfect space-based mirrors continues to drive advances in precision engineering, materials science, and our understanding of the physics that governs electromagnetic radiation in extreme environments. As we look toward the future, the possibility of manufacturing perfect or near-perfect mirrors in space, using resources and conditions unavailable on Earth, becomes increasingly intriguing. The perfect vacuum, unlimited size scales, and freedom from gravity might enable mirror fabrication techniques that push closer to theoretical perfection than anything possible in terrestrial laboratories. Whether through advanced human technology or natural cosmic processes we have yet to understand, the universe continues to provide surprises that challenge our understanding of what's possible. Each new discovery in astronomy and cosmology adds to our knowledge of how electromagnetic radiation behaves under extreme conditions, informing our quest to understand the ultimate limits of reflection and the fundamental principles that govern light-matter interactions. From the smallest quantum mechanical effects in laboratory metamaterials to the largest structures in the observable universe, the physics of reflection reveals deep connections between apparently unrelated phenomena. The cosmic perspective reminds us that our earthbound experience of mirrors represents just one small corner of a vast parameter space where electromagnetic radiation encounters matter under every conceivable condition. As we prepare to conclude our journey through the physics of perfect mirrors, these cosmic considerations provide essential context for understanding both the possibilities and limitations that govern reflection in our universe. They remind us that the pursuit of perfect mirrors is ultimately a quest to understand fundamental principles that operate on scales from the quantum to the cosmic, connecting the behavior of individual photons to the structure and evolution of the universe itself. Throughout human history, mirrors have served as far more than mere tools for seeing our physical appearance. They have functioned as profound symbols that illuminate our deepest questions about reality, truth, identity, and the nature of existence itself. From the polished bronze mirrors of ancient civilizations to the silvered glass hanging in modern homes, these reflective surfaces have consistently captured human imagination in ways that transcend their practical utility. Now, as we contemplate the possibility of perfect mirrors that reflect light without any loss whatsoever, we find ourselves confronting questions that reach to the very heart of what it means to exist in a universe governed by physical laws. The metaphor of reflection permeates human language and thought in ways that reveal our intuitive understanding of mirrors as gateways between reality and representation. When we speak of reflecting on an idea, we invoke the image of thought bouncing back to us from some invisible surface, returning with new clarity or understanding. The phrase mirror image suggests perfect duplication, while smoke and mirrors implies deception through clever manipulation of appearances. These linguistic habits point to something deeper about how mirrors function in human consciousness. They serve as bridges between the subjective experience of self-awareness and the objective reality of physical existence. When you look into a mirror, you simultaneously see yourself as others see you and experience the strange recursion of consciousness observing itself. This dual nature has made mirrors central to philosophical discussions about the relationship between mind and matter, between observer and observed. Ancient Greek philosophers used mirror metaphors to explore fundamental questions about knowledge and reality. Plato's famous allegory of the cave describes prisoners chained to face a wall, seeing only shadows of real objects cast by firelight behind them. The shadows serve as imperfect reflections of reality, just as ordinary mirrors show us reversed images of the world. Plato suggested that our everyday experience might be like looking at shadows or reflections, giving us only indirect access to ultimate truth. The perfect mirror we've been exploring throughout this journey represents the logical extreme of Plato's metaphor. If ordinary mirrors give us imperfect reflections of reality, distorted by losses and limitations of physical materials, then a perfect mirror would provide perfect reflection, preserving every detail of the original with absolute fidelity. Such a mirror might serve as a metaphor for perfect knowledge or perfect understanding, where truth is reflected without distortion or loss. But this perfection comes with its own philosophical puzzles. Perfect reflection implies perfect preservation of information, yet our exploration of physics has suggested that such preservation might be fundamentally impossible in our universe. The second law of thermodynamics ensures that entropy increases over time, meaning that information and organization gradually degrade. Perfect mirrors seem to violate this universal tendency toward disorder, creating islands of perfect preservation in an ocean of increasing chaos. This tension between the desire for perfect preservation and the reality of universal entropy reflects deeper human anxieties about mortality and meaning. We create art, literature, and monuments in attempts to preserve something of ourselves for future generations, yet we know that everything we build will eventually crumble. Perfect mirrors, if they could exist, might represent the ultimate victory over entropy, a way to preserve light and information indefinitely. Religious and mystical traditions have long associated mirrors with revelation and enlightenment. In many cultures, reflective surfaces are believed to reveal hidden truths or provide access to spiritual realms. The ancient practice of scrying involves gazing into polished surfaces to receive visions or insights. Islamic art developed sophisticated geometric patterns that seem to reflect infinitely in complex symmetric arrangements, suggesting mathematical harmony underlying spiritual reality. The concept of a perfect mirror resonates with these spiritual traditions in profound ways. A surface that reflects light without any loss might be seen as approaching the divine, transcending the limitations that constrain ordinary matter. The perfect preservation of information in such a mirror could symbolize eternal memory or consciousness that persists beyond physical death. Buddhist philosophy includes the metaphor of the mirror mind, a state of consciousness that reflects all phenomena clearly without distortion or attachment. This mental mirror is said to be naturally pure and luminous, capable of perfect awareness when not clouded by ignorance or desire. The perfect mirror we've been exploring might serve as a physical metaphor for this ideal state of consciousness, reflecting reality with perfect clarity and completeness. Yet the very perfection of such reflection raises questions about the relationship between original and copy. If a perfect mirror preserves every aspect of incident light with absolute fidelity, is the reflected image somehow equivalent to the original? This question echoes ancient puzzles about identity and duplication that have puzzled philosophers for millennia. Consider the ship of Theseus paradox, which asks whether a ship remains the same ship if all its parts are gradually replaced. Applied to perfect mirrors, we might ask whether perfectly reflected light is the same light that originally struck the mirror, or whether it's a perfect copy that merely carries the same information. The distinction matters for questions about consciousness and identity. If perfect reflection preserves all information, could consciousness itself be perfectly reflected or copied? Modern technology has made these philosophical puzzles increasingly practical. Digital copying allows perfect duplication of information, raising questions about ownership, authenticity, and identity in the information age. Perfect mirrors might represent the physical analog of perfect digital copying, preserving electromagnetic information with the same fidelity that digital systems preserve data. The cultural impact of mirrors extends far beyond philosophy into art, literature, and popular imagination. Mirrors feature prominently in fairy tales and folklore, often serving as magical objects that reveal truth or transport characters to other realms. Snow White's magic mirror speaks truth about beauty, while Alice's looking glass opens a portal to Wonderland. These stories reflect deep human intuitions about mirrors as boundaries between reality and possibility. In literature, mirrors often symbolize self-knowledge and psychological depth. The mirror phase in psychoanalytic theory describes the moment when children first recognize themselves in mirrors, marking a crucial stage in the development of self-awareness. This recognition of the self as an object that can be observed from outside represents a fundamental step in human psychological development. Perfect mirrors might represent the ultimate achievement of this self-reflective capacity. A mirror that preserves every detail of reflected light could serve as a metaphor for perfect self-knowledge, where consciousness sees itself with complete clarity and understanding. Yet such perfect self-reflection might also be psychologically overwhelming, revealing aspects of self that are normally hidden or filtered by the limitations of ordinary perception. The myth of Narcissus, who fell in love with his own reflection in a pool of water, warns of the dangers of excessive self-reflection. Perfect mirrors might amplify this risk, creating reflections so compelling and complete that they become more attractive than reality itself. The perfect preservation of visual information might trap consciousness in endless loops of self-observation, preventing engagement with the wider world. Art has long used mirrors to explore questions of reality and representation. The famous painting Las Meninas by Diego Velázquez includes a mirror that reflects figures who are presumably standing where the viewer would be, creating a complex interplay between representation and reality. Modern and contemporary artists continue to use mirrors to question assumptions about perception and truth. Perfect mirrors would offer artists unprecedented opportunities to create works that preserve and manipulate light in ways that approach the permanence traditionally associated with painting or sculpture. Light itself could become a sculptural medium, trapped and shaped within perfect mirror installations that maintain their luminous properties indefinitely. The scientific quest for perfect mirrors also reflects deeper human drives toward perfection and transcendence. The pursuit of ever better reflectivity parallels other human efforts to overcome natural limitations, from the development of flight to the conquest of disease. Perfect mirrors represent a kind of technological transcendence, where human engineering overcomes the fundamental tendency of matter to absorb and scatter electromagnetic radiation. Yet our exploration has suggested that perfect mirrors might be impossible due to fundamental physical principles. This impossibility might itself carry philosophical significance, suggesting that some forms of perfection are inherently beyond reach. The asymptotic approach toward perfect reflection, where each improvement becomes progressively more difficult, might serve as a metaphor for the human condition itself, always striving toward ideals that remain just beyond grasp. The economic and social implications of perfect mirrors would be profound if they could somehow be created. Such devices would revolutionize solar energy, laser technology, and optical communications, potentially transforming human civilization. But they might also exacerbate inequality if the technology were difficult to produce or control. Perfect information preservation could enable unprecedented surveillance capabilities, raising questions about privacy and freedom. These social considerations remind us that technological perfection always exists within human social contexts that shape its meaning and impact. Perfect mirrors, like any powerful technology, would be embedded in networks of power, ownership, and control that determine who benefits from their capabilities. The environmental implications are equally complex. Perfect mirrors would enable highly efficient solar energy systems that could help address climate change, but their production might require materials or processes with significant environmental costs. The perfect preservation of electromagnetic energy could reduce waste in optical systems, but it might also enable new forms of energy consumption that offset these gains. As we contemplate these broader implications, we're reminded that the quest for perfect mirrors is ultimately a human endeavor, driven by human desires and shaped by human values. The physics of perfect reflection connects to fundamental questions about perfection, permanence, and possibility that have concerned humans throughout history. The mirror hanging in your bathroom this morning reflects not just your physical appearance, but also thousands of years of human curiosity about light, reflection, and the nature of reality itself. From polished obsidian used by ancient civilizations to the hypothetical perfect mirrors we've explored, each advance in mirror technology has been accompanied by new questions about what it means to see clearly and preserve truth. Whether or not perfect mirrors prove ultimately possible, the effort to understand them illuminates the deep connections between physics and human experience. The electromagnetic radiation that bounces from mirror surfaces carries not just energy and momentum, but also information about the world around us. In seeking to preserve this information perfectly, we're expressing fundamental human desires to understand, remember, and transcend the limitations that define our existence. In the end, the perfect mirror serves as both a scientific goal and a philosophical symbol, representing humanity's eternal quest to see clearly and preserve what matters most. As we prepare to conclude our journey through the physics and metaphysics of perfect reflection, we carry with us not just technical understanding, but also deeper appreciation for the ways that scientific inquiry connects to the most profound questions about reality, consciousness, and what it means to be human in a universe governed by physical law. As our journey through the physics of perfect mirrors draws to a close, we find ourselves standing at the edge of a profound realization. The perfect mirror we have explored in such detail, this hypothetical surface that reflects 100% of incident light with no absorption, no scattering, no loss of any kind, may represent something far more significant than a mere technological goal. It may embody the ultimate expression of humanity's desire to transcend the fundamental limitations that govern our physical universe, a desire that reveals as much about the nature of human consciousness as it does about the laws of physics. Throughout our exploration, we have encountered hints that perfect reflection might be impossible, not merely difficult or technologically challenging, but fundamentally prohibited by the deepest principles that govern reality. The second law of thermodynamics demands that entropy increase in any closed system, yet perfect mirrors seem to preserve electromagnetic order indefinitely. Quantum mechanics introduces unavoidable uncertainty and vacuum fluctuations that appear to prevent the perfect deterministic response required for lossless reflection. The very atoms that would constitute a perfect mirror are subject to thermal motion and quantum uncertainty that makes their behavior inherently probabilistic rather than perfectly predictable. These are not merely technical obstacles that clever engineering might overcome. They represent fundamental features of our universe that may make perfect reflection impossible in principle. The uncertainty principle ensures that we cannot know both the position and momentum of particles with perfect precision, which means that electrons in a mirror surface cannot respond to electromagnetic fields with the perfect predictability that lossless reflection would require. Thermal fluctuations guarantee that atoms in any material at finite temperature will be in constant random motion, introducing noise and disorder that degrades perfect electromagnetic responses. Even at absolute zero temperature, quantum zero-point motion ensures that particles never come completely to rest, maintaining a residual motion that prevents perfect order. The quantum vacuum itself presents perhaps the most fundamental limitation. Even empty space contains virtual particle pairs that spontaneously appear and disappear, creating electromagnetic field fluctuations that interact with any material surface. These vacuum fluctuations represent an irreducible source of noise that might prevent perfect reflection, regardless of how carefully materials are prepared. Yet the impossibility of perfect mirrors does not diminish their value as theoretical constructs. Like other idealized concepts in physics, the perfect mirror serves as a limiting case that helps us understand the behavior of real systems. Just as the concept of a perfect gas helps us understand real gases despite the fact that no gas perfectly obeys the ideal gas law, perfect mirrors illuminate the principles governing reflection, even though perfect reflection may be unachievable. The pursuit of ever better mirrors has driven remarkable advances in materials science, quantum optics, and precision engineering. Each step toward higher reflectivity has revealed new physics and enabled new technologies. Gravitational wave detectors like LIGO rely on mirrors with reflectivities exceeding 99.9997% to detect distortions in space-time smaller than 10 to the -18 meters. These instruments have opened an entirely new window on the universe, revealing colliding black holes and neutron stars through their gravitational signatures. Advanced laser systems use nearly perfect mirrors to achieve unprecedented precision in timekeeping, distance measurement, and fundamental physics experiments. Atomic clocks accurate to 1 part in 10 to the 18th power, quantum computers that manipulate individual atoms with laser light, and experiments that test the foundations of quantum mechanics all depend on mirrors that approach theoretical limits of reflectivity. The quest for perfect reflection has also deepened our understanding of the relationship between information and physics. Perfect mirrors would preserve information carried by electromagnetic radiation with complete fidelity, raising questions about the fundamental limits of information, processing, and storage. These questions connect to deep problems in theoretical physics, including the information paradox in black hole physics, and the relationship between quantum mechanics and general relativity. Even if perfect mirrors prove impossible, the asymptotic approach toward perfect reflection continues to yield insights and applications. Each improvement in mirror technology, each fractional percentage point increase in reflectivity, enables new capabilities and reveals new physics. The journey toward perfection may be more valuable than reaching the destination itself. The mathematical beauty of perfect reflection also deserves recognition. The equations describing electromagnetic waves interacting with perfectly conducting surfaces exhibit elegant symmetries and conservation laws that illuminate deep connections between seemingly disparate physical phenomena. Maxwell's equations, when solved for perfect boundary conditions, reveal the fundamental unity underlying electricity, magnetism, and light itself. This mathematical elegance suggests that perfect mirrors occupy a special place in the theoretical framework of physics, even if they cannot exist in reality. They represent points of perfect symmetry in the space of possible electromagnetic behaviors, singular configurations that help define the boundaries of what is physically possible. The philosophical implications of impossible perfect mirrors extend far beyond physics. They remind us that human aspirations often exceed the possibilities allowed by natural law. Yet this excess is itself a source of creativity and progress. The gap between what we can imagine and what we can achieve drives scientific inquiry, artistic expression, and technological innovation. Perfect mirrors serve as metaphors for other impossible human ideals: perfect justice, perfect truth, perfect understanding. Like these moral and intellectual aspirations, perfect mirrors may be unattainable in reality, while remaining valuable as guiding principles that shape our efforts and direct our progress. The impossibility of perfect reflection also illuminates the relationship between perfection and existence. Our universe appears to be characterized by fundamental trade-offs and limitations that make perfect efficiency impossible in any real process. The speed of light limits information transfer. Quantum uncertainty limits simultaneous knowledge of complementary properties, and thermodynamic principles limit the efficiency of energy conversion. These limitations are not flaws in the design of reality, but may be essential features that enable the complexity and richness we observe. A universe with perfect mirrors might also be a universe without the imperfections and asymmetries that enable stars to shine, planets to form, and life to evolve. The very impossibility of perfect reflection might be connected to the possibility of existence itself. Yet science fiction and theoretical physics continue to explore scenarios where perfect or near-perfect mirrors might exist under exotic conditions. Some theories of quantum gravity suggest that space-time itself might have reflective properties under extreme conditions. Cosmic strings, hypothetical one-dimensional defects in space-time, might act as perfect mirrors for certain types of radiation. The surfaces of higher dimensional objects, if they exist, might exhibit perfect reflection when viewed from our three-dimensional perspective. These speculative possibilities remind us that our understanding of physics remains incomplete. The standard model of particle physics and general relativity, our best current theories, have been tested extensively but may not represent the final word on the nature of reality. Future discoveries might reveal new possibilities for controlling electromagnetic radiation in ways that approach or achieve perfect reflection. Advanced civilizations, if they exist elsewhere in the universe, might have developed technologies that approach perfect reflection more closely than anything we can currently imagine. The search for extraterrestrial intelligence sometimes considers the possibility that alien technologies might create detectable signatures in electromagnetic radiation, including perfectly reflected signals that would stand out against natural cosmic backgrounds. Even on Earth, emerging technologies continue to push the boundaries of what's possible in optical reflection. Metamaterials with engineered electromagnetic properties, quantum dots with controllable energy levels, and topological materials with protected surface states all offer new approaches to achieving ultra-high reflectivity. While perfect reflection may remain impossible, the definition of nearly perfect continues to evolve. The practical applications of nearly perfect mirrors extend far beyond current technology. Space-based solar power systems could use ultra-high reflectivity mirrors to concentrate sunlight with unprecedented efficiency. Optical quantum computers might use nearly perfect mirrors to create stable quantum states that persist for arbitrarily long times. Advanced laser propulsion systems could accelerate spacecraft to significant fractions of the speed of light using nearly perfect mirror sails. These applications remind us that the impossible often serves as a useful target for human effort. The pursuit of perfect mirrors, even if ultimately unsuccessful, continues to generate technologies and insights that transform human capabilities. The journey toward impossible goals often proves more valuable than reaching the goals themselves. As we conclude our exploration of perfect mirrors, we're left with a profound appreciation for the intricate relationships between physics, philosophy, and human aspiration. The electromagnetic radiation that surrounds us every moment carries information about the universe in forms that we're only beginning to understand. Our ability to control and manipulate this radiation through reflection represents one of humanity's most sophisticated achievements, connecting us to fundamental principles that govern everything from atomic structure to cosmic evolution. The perfect mirror remains impossible, a shimmering ideal that recedes as we approach it, always just beyond the reach of our finest engineering and deepest understanding. Yet in chasing this impossible perfection, we have learned to see light itself more clearly, to understand the quantum mechanical foundations of matter, and to appreciate the subtle interplay between information, energy, and entropy that shapes our universe. Perhaps this is the ultimate lesson of the perfect mirror, that in pursuing the impossible, we discover new possibilities. In seeking perfect reflection, we learn to see more clearly. In chasing ideal efficiency, we develop better technologies. In contemplating perfect preservation, we appreciate the delicate impermanence that makes existence precious. The light that strikes your bathroom mirror this morning carries with it the history of the universe, from the cosmic microwave background radiation that fills all space to the nuclear fusion reactions in our sun's core. The reflection you see, imperfect though it may be, connects you to electromagnetic phenomena that span scales from the quantum to the cosmic. In that reflection lies not just your image, but a window into the fundamental principles that govern light, matter, and consciousness itself. And so our journey ends where it began, with light meeting mirror in an interaction that seems simple but reveals infinite depth. The perfect mirror may be impossible, but our quest to understand it has illuminated the hidden rules by which our universe operates. In chasing perfection, we have learned that the true beauty lies not in achieving the impossible, but in the understanding that emerges from the pursuit itself.